Hello, my dear students, and welcome back to the third and the final part with our first lecture titled by Introduction to Semiconductor Material. As I mentioned, it's a briefing chapter to start our devices, starting with the PN junction. Now, in this lecture, we are going to focus on the difference between degenerate and non-degenerate semiconductor material. Then we are going to illustrate something about recombination effect. And finally, we are going to discuss in a brief manner the drift diffusion model, which is a key pillar in our semiconductor devices course. Now, let me share my presentation slide and start the third part of lecture number 1. Okay, I believe now you can see my presentation slides, and also let's start operating the laser pointer as well. Okay, perfect. Okay, perfect. So this is lecture number 1. I think in our part number 2, we have reached the intrinsic and extrinsic semiconductor materials, where we have the doping effect, as you can see. Yeah. Okay. So I think this was our final slide for part number 2. When we say that we have 3 types of material: intrinsic, which is the extreme left figure, where we have number of electrons equals to number of holes, and the Fermi level is directly in the center of the energy gap. An n-type extrinsic semiconductor, electrons are more than holes, and the Fermi level starts to move toward the combination band, which is reflects the higher amount of electrons. And finally, the extreme right figure, where we have holes greater than electrons, and the Fermi level goes downward to the valency band, where indicates that holes is greater than or holes are greater than electrons. Okay. Now, based on our previous knowledge, we can say that the Fermi level position is a function in doping. This is clearly observed here. Here, yes, I'm sorry. Here, when you increase the n-type doping, your Fermi level starts to go upward, while when you increase your p-type doping, your Fermi level starts to go downward. That mainly reflects that the Fermi level is a function in doping. So the higher the doping, the n-type doping, for example, the higher the Fermi level, or the nearer the Fermi level to the conduction band, and the higher the p-type doping, the nearer the Fermi level to the valency band. Herein, we can classify our doping effect into 2 main sets. When the doping is, or when the doping reflects on the Fermi level, so that the distance between the Fermi level and the combination conduction band, or the distance between the Fermi level and the valency band is 3 kT or less, then we will call this as a degenerate semiconductor. In other words, when you increase the doping effect so that your Fermi level starts to be very close to the conduction band, or starts to be very close to the valency band, then this is a special case of doping, or a special case of semiconductor, which is called a degenerate semiconductor. Otherwise, when you have doping, but the distance between the Fermi level and the conduction band, or the Fermi level and the valency band, is greater than 3 kT, we call this the non-degenerate case. Normally speaking, in 95, 96, 97% of the case, we are dealing with non-degenerate semiconductor. Especially in our course, we will roughly have a non-degenerate semiconductor all over the time. However, in some special applications, some special cases, maybe you can know one of these applications is the semiconductor lasers, for example. You need to have a degenerate semiconductor. This may be considered in other coming courses, inshallah. However, for the current study, as I mentioned, most of the cases, it will be a degenerate semiconductor. Sorry, a non-degenerate semiconductor. Okay, perfect. Another important issue, I just need to refresh your memory with it, which is the direction of energy. What do I mean by direction of energy? We know that we have a Fermi level, we have a valency band, we have a conduction band. So, roughly speaking, whenever you go upward, the energy increases. That's why when you have an electron in the valency band and this electron gains some energy, electron jumps from the valency band to the conduction band, which means that electron go to a higher state of energy, which is typically, I believe we did this, I think, here, yes, not here. Yes, here, typically, yeah. This electron gain some internal thermal energy, so its energy increase so that the electron jump from a lower energy state, or energy band, which is the valency band, to a higher energy state or an energy band, which is the conduction band. So the higher the band, the higher the energy. Makes sense. That means that the direction for energy is upward. I mean, if this electron gain more energy, it will go more and more upward. If it loses energy, it will go downward. That's typically true. However, we need to refresh your memory with a very important knowledge regarding the direction of energy, which is that the direction of the energy of hold is counter to the direction of energy of electrons. I mean, if the direction of the energy of electrons is upward, which is the same example I just demonstrated, then for holes, the direction of energy is downward. This example, we solved it together 2 semesters ago, when I told you which of these holes has a higher energy, number 3 or number 4. Then your answer should be that hole number 4 has a higher energy than hole number 3. This will be more and more clear when we go to the drift diffusion model a few seconds from now. But what is important for us now is that whenever the energy of electrons increase upward, that means that the energy for holes increase downward. Okay. Then let's do what's called the thermal equilibrium condition. As I just mentioned, that for a thermal equilibrium condition, electrons can move from valency band to the conduction band. However, it's very important to know that as far as we are under thermodynamic equilibrium condition, mass action law, the very famous mass action law, I believe you use it in electronics 1 and electronics 2, in materials, you use it more than 2 or 3 times before in your module. This famous mass action law, N times V equals Ni squared, exists. What is the thermal equilibrium effect or thermodynamic equilibrium condition? The thermodynamic equilibrium condition is simply that this material or this device has no external applied force. Normally, external applied force in our case comes from potential energy, from potential source. I mean, when you apply a potential, a bias, a voltage on the device. As far as there is no voltage applied to the device, that means that you are under thermodynamic equilibrium and you can freely use the mass action law, which is N times P equals Ni squared. This is very important, my dear students. When there is external applied voltage on the device, no thermodynamic equilibrium exists. The question will be, how I can know from the energy band diagram that there is a thermodynamic equilibrium? I have an energy band diagram like this, with a valence band, conduction band, Fermi level, all these stuff. How can I detect if I am under thermodynamic equilibrium or not? The answer is very simple. Please look at the Fermi level. If the Fermi level is a horizontal line, like that, the one you see now, this dotted red line, then automatically this is under thermodynamic equilibrium. Whenever there is a tilting or a shifting in the Fermi level, then there is applied voltage. We will make it in more detail when we go to the drip diffusion model and later on when we are tackling our different devices. Perfect. Okay, so what about non-equilibrium conditions? We say that the equilibrium conditions reflect where n times b equals to I squared. This is the equilibrium. So obviously, non-equilibrium conditions mean that n times b not equals to ni squared. And here we have two cases. When n times b is greater than ni squared, or when n times b is smaller than ni squared. The first case is what's called carrier generation. It makes sense. You are increasing the rate of the carrier with respect to the normal rate. So you have some sort of injection. Most probably this will be, for example, optical injection. This happens in case of solar cells, for example, when you receive energy from light, from the solar light. So you have a carrier generation, and in this case, this is not a thermodynamic equilibrium. You have an external source of energy, and then n times b is not or is greater than ni squared. This is the first case. Or you have what's called a recombination effect. The recombination effect means that your carriers are decaying so that n times b is smaller than ni squared. And this is what I'm going to illustrate briefly in this slide. What is the recombination effect? Basically, recombination is the anti-process of the generation. So we have first to know what is generation. Generation simply is this process. When electrons leave the valency band and go to the conduction band, we call this generation. Why this is a generation? Because in this case, if I ask you how many free electrons you have, you will answer 0. I don't have electrons in the conduction band. How many holes do you have? You will answer also 0. You don't have any broken bond in the valency band. But due to this thermal energy, which is still internal, one electron hole pair has been generated. So electron move the valency band to the conduction band. Now you have one free electron in the conduction band, and you have one broken bond, one hole in the valency band. Then you have generated an electron hole pair. By the way, you can generate electrons without holes, like the case of n-type doping. And you can generate holes without electrons, like the case of p-type doping. So we call this as the generation process. As I mentioned, you can generate electron and hole pairs, you can generate electrons only, or you can generate hole only. However, all these generation processes, whenever it's internal process, I mean either due to internal thermal energy or due to doping effect, we call it an internal process. Whenever this generation process is externally implemented to the material, like the case of optical injection, for example, in this case, we call this an carrier generation or optical generation. Of course, if it's optical, and in this case, n times p is greater than ni squared. Now, what is the inverse process? I mean, whenever you have an electron in the conduction band, and for a reason or another, this electron loses its energy, maybe in a scattering process, in a collision process, or whatever. Then, electron will make its round trip back. I mean, the electron will go back to the valency band, and it will produce this difference in energy in a form of another wave energy. Typically, we have here two cases or two probabilities, either to lose this energy in a form of photons, which is the quanta for light energy, or to lose this energy in a form of phonons, which is the quanta for the thermal or the heat energy. So In this case, we call this process, which is the inverse process of the degeneration, we call this as the recombination process. Whenever electron recombine back to the hole. Here we have different scenarios for recombination. The first we will call the band-to-band recombination. I mean, it's directly mean that electron can leave the valency conduction band and go directly to the valency band in one stop and then emit either light energy or heat energy. This is what's called band-to-band recombination. Other way of recombination is to have an intermediate step. Herein you should ask yourself how to have an intermediate step in the energy band gap. An energy band gap, theoretically, is a gap where there is a forbidden states. However, due to impurities, some trapping states can occur in the forbidden band gap. In this region, in this case, electron can drop in two stops. First, from the combination band, or from, sorry, the conduction band to the trapping state, and then from the trapping state to the valency band. And this is what's called the trap-associated recombination. Most probably, in this case, the emitted energy is in the form of phonon, which is again the quanta for a thermal energy. So in this case, we have what's called the trap-associated recombination. The final case is what's called the Auger recombination. This is usually due to collision. When two electrons collide together so that one electron transfers its energy to the other and go down to the valency band. So in this case, you don't have either a photon or a phonon emission because the energy, the potential energy inside the electron is transferred totally to another electron, and the first one return back to the valency state or the valency band. These are the three main scenarios for recombination in semiconductors. Let's now turn to the most important part in this lecture, which is the drift diffusion model. Why this is the most important part? Because basically, in any electronic device, especially those we are going to demonstrate in our module, we are going to express the IV relationship or the JV relationship using the drift diffusion model. So this model will extend with us along all the devices that we are going to demonstrate in this module. So let's start with what is the drift diffusion model. Simply, what we are trying to do is that we are searching for an equation for the current flowing in a device or in a material, whatever. So let's start with the scratch equation for current. This equation saying that I, or the current, sometimes we call it J, which is the current density, I mean ampere per unit area, is equals to dq by dt. Now, you should know that Q is defined as the term free carrier. Free, it means that it is not bounded to the nucleus, and carrier to include both electrons or holes. So whenever you have a free carriers, which means free electrons in the conduction band or free holes in the valency band or both, then you can have electrical current. But this is not the only restriction, or this is not the only condition to have an electrical current. Another condition is represented in d by dt, that this free carrier should move with respect to time in what we call a guided motion. So in order to have electrical current, you should have two main conditions. The first is to have a free carrier. These free carriers have actually three scenarios. Either you can roll on the natural free carrier due to the internal thermal energy, what we call the intrinsic concentration. This is the free carrier. You can increase the electrons if you make an n-type doping, or you can increase the holes if you make a p-type doping. That's what we call the free carriers. But these carriers so far are static carriers. They are not moving in a guided way. So the second condition is to have what's called the carrier transport. This carrier should have a guided motion toward a certain direction. And this is implemented either by drift or diffusion. That's why we call this a drift diffusion model. Let's start with the drift current. So if we have a semiconductor, let's say that we have an intrinsic semiconductor. That's why we have the Fermi level directly in the center of the energy band gap. Then you have, for example, a free electron in the conduction band. Perfect. What if you connect this semiconductor material with an external bias, an external source of energy, an external voltage? Now, please remember, my dear students, that once you connect your material or a device with an external voltage, you lose the thermodynamic equilibrium condition, if you remember. So, from our basic understanding of physics, we know that electron is a negative charge, and this battery has an electrode or a terminal here is positive. So logically, this electron should move in the right direction to be attracted to the positive terminal of the battery. Then how we can reflect this on the energy band diagram? It's very simple. This will happen. You will find that there is a tilting in the energy band diagram. That's why electron will move to the positive terminal of the battery. Why electron move? You can say that electron move because there is a positive terminal here. Or you can say that whenever you have a tilting like that, that means that the energy here is less than the energy zero. And based on the minimum potential theory, any particle is acting to go to the minimum potential state. So in this case, you can find that this electron will move to go to this state to have a minimum potential, because the potential here is smaller than the potential energy, is smaller than the potential at this point. Similarly, please remember the energy of the hole is in the counter direction to the energy of the electron. So if this state from the electron point of view is lower than this one, from a hole point of view, this state is lower than this state. Again, because the whole energy increased to downward. Accordingly, hole will go to the left direction, which again makes sense because you have a negative terminal of the battery here in the left side. So electron move from left to right, hole move from right to left. And this is the indication that we have what's called a guided motion, or what's called a carrier transport. That's why whenever you connect a semiconductor with a voltage, you have a current, and this current is due to the drift carrier transport, either electrons or holes. Now, if we would like to express this in a form of equation, we can use this equation. Here, the J, which is the current density, the current per unit area again, equals 2. One part is due to electrons and the other is due to holes. For the one due to electrons, we have three main terms. The first is N, which is basically the number of electrons in the conduction band, or the number of free electrons. Q, of course, is a constant. And Vd, which is the drift velocity, I mean the velocity at which these electrons move from left to right. It is very makes sense to have this V. Why? Because when we first define current, we say that current is proportional to d by dt, the rate of a change with respect to time. And as you know from your mechanics classes, d by dt is the term representing velocity. So this Vd is equivalent to the d by dt term. Here we use the letter D to indicate that this is a drift velocity due to a battery, and we indicate also the term N to indicate that this is the velocity of electron. May you ask now a question? Does the velocity of electron equals to the velocity of holes? The answer simply is no. Why? Because this drift at velocity equals to mu, which is the mobility, times by eta, which is the electrical field. And as we just mentioned in the beginning of this lecture, or maybe in the last part, that the mobility of electrons and the mobility of holes are not equal. That's why we say that the mobility of electrons is higher in silicon, exactly. So that's why mu n is greater than mu p, then Vd n is greater than Vdp. And eta, or the electrical field, depends on the battery you have. The higher the electrical field, I mean the higher the voltage, the higher is the velocity, which is again makes sense because whenever you increase the velocity, this tilting starts to increase more and more. So the electron will drift as well as holes in a higher speed. So this term represents what's called the drift current. It is very important to recognize that drift current is a main function in eta, or in the electrical field. If eta is equal to 0, you don't have a battery like this. You don't have a drift current. You will have only a drift current if you have eta. So the sign for drift current is to have an external battery, an external voltage source, which is an electrical field or eta. This is an old relation we have already discussed in the previous course in the material, saying that the mobility is inversely proportional to the mass. Again, this very makes sense because whenever the particle is with a higher weight, its mobility decreases. So very makes sense. Okay, this what we call the drift current. We can sum up, or first we can take an eta as a common factor, and we can sum up all these terms, I mean n q mu n plus p mu q mu p in what's called sigma. Do you remember the first slide in this lecture? When we measure sigma in lab, the conductivity, this is sigma, which is the mobility times the number of carriers times the q for electrons and holes. This is basically, my dear students, is Ohm's law. J equals sigma E is typically V equals I times R. This is typically Ohm's law. Okay. You can have some special cases for this sigma. When the material is an n-type material, so number of electrons is greater than the number of holes, so you can easily eliminate the p part, and you can say that sigma is equals to n q mu n. Similarly, if the material is a p type, you can eliminate the n type and say that sigma equals to q times b times mu p. So this is a special condition whenever the material is n type or a p type, or you can of course use the general formula for sigma whenever it's an intrinsic, or n and b are somehow equal. Okay, so this is what's called the drift current. What is the other format for a current? It's what's called the diffusion current. What is a diffusion current? Let's have it together. Okay. Let's assume that for some reason or another, your carriers are not uniformly distributed in the material. I mean, you have a region where you have a huge amount of carriers, and you have another region where carriers are very low. These carriers may be, of course, electrons or holes. Then we will have what's called diffusion current. Diffusion current, my dear students, is simply the flow from the high concentration region to the low concentration region. For example, let's assume that you have two water tanks, and the level of water in one is higher than the next, and you open the valve. Then water will flow from the higher level to the lower level. This is typically what happens in the diffusion current. So current diffused from one region to another.